Let me introduce Dr. Ted Gifford from Schneider National. His team addressed a complex problem of freight transportation that occurs in bulk chemical transport.
Thank you. Thank you, Patricia. So I'll talk about a dispatch optimization problem. Our project team, the first four of us are from the engineering and advanced analytics group at Schneider National. Andy is from our software development solution team, and Rob Randall is from Princeton Consultants. And at the end, I'll talk about some other people who contributed in various ways, but these are the principal authors. So I'll just give you a bit of background about Schneider and kind of the transportation industry that we're in. Then I'll talk specifically about the problem that we're addressing here. Then go into our modeling approach, and then Ashish will take over and talk about the details of the solution technique. And then we'll talk about some implementation details, and then the results, which are really the business benefits, and some thoughts about some specific things that we're going to continue to evolve with this model. So just a bit about Schneider. We just became a public company this last spring, founded in 1935 when Al Schneider sold his car and bought a truck, and continued to grow over the years. We're one of the largest transportation companies in terms of full truckload freight. Our loaded trucks circle the globe an equivalent of 360 times a day. A couple of other things that are important to note. We've got about 13,000 trucks that run around the country, close to 50,000 trailers of various types that haul various products. The particular problem that I'm going to talk about is in the transport of chemicals and fuels, and these range from diesel fuel, avgas, the solutions that are used to de-ice airplanes at airports, raw materials that go into the production of paint, finished products like paint. We don't haul food grade products at all, but it's all in this chemical area. We do it with about 1,000 tractors and drivers, about 1,600 tankers and trailers. We process approximately 1,800 orders per week. Now, there are a couple of very interesting related problems that I won't talk about, and that is deciding which 18 orders out of anywhere from 2,200 to 3,500 orders a week that might be presented to us based on what the economic conditions currently are. Now, one interesting thing, when we built this system, freight was fairly soft, and now we're in a very good freight market, and we've found that this system has been resilient and adaptive to changes in market conditions. So one thing to point out to people that have at least a passing understanding of transportation networks and supply chains is that a random one-way network is very different than the kind of transportation you would experience with FedEx or UPS or an LTL company, because what happens is whenever a tractor and a driver moves from one position to another, or a trailer moves from one position to another, your network has changed, your capacity has changed, and the configuration of your resources have changed. So you have to constantly be thinking about not only how profitable is it to do something, but how profitable is the state of the network when you arrive at that destination. So about 350 orders a day. When an order is accepted and we go to execute that order, it requires us to determine an appropriate tanker trailer to move that product, as well as one or more truck drivers to haul that trailer to various spots. And as I'll show in a minute, it typically takes at least 3 distinct moves of the tanker to affect the order. Typically, We have, as I said, we have about 1,600 tankers. There are actually about 100 distinct configurations, so they can be lined with fiberglass or aluminum or steel or some other special compounds. The products that go into the trailers can be highly toxic chemicals, so we have to pay attention to not only what is in the tank now, but what was in the tank up to 3 prior movements of that tank with customer orders. So I'll talk a little bit about the product compatibility business rules model that is just a precursor to the optimization. Typically we try to assign the trailers about 4 days before the pickup of the order, but as you'll see when Ashish goes through a iterative process that our optimization uses, quite often that preliminary assignment will be replaced with a better assignment when we actually figure out who the driver will be that's associated with part of the shipment. And drivers, we have to pay attention to some different work configurations, their work schedules, the DOT rules related to how many hours drivers can drive. We have to pay attention to what certifications they have, hazardous materials, the certification to enter and exit nuclear facilities, and those kinds of things. So here's kind of a simple example of what the dispatch optimization problem starts to look at. We've got some pickup locations and delivery locations for customers and some locations where these tanks will be washed. And I'll talk about that a little bit more. But basically, the tanks have to be washed between almost every order. Now, sometimes if it's exactly the same product from the same customer and it's a product that doesn't either decay or harden over time, you can get by without a tank wash. But the predominant situation is wash, pick up, deliver, go wash again. So we start with a customer order, and initially we'll determine a prospective wash location, and this is a fairly simple assignment problem. We can look at various kinds of costs and distance and whatnot, and then we have to figure out where to send the tank after it delivers the product so it can be washed again to move on to its next order. And so that's what a kind of a simple chain looks like. But when we get into an optimization problem, we start to see that there are other options that come into play that need to be thought of from a global perspective. So for example, in this particular case, a tanker that could have come from wash site 1 to pick up at location 1 may have looked the best locally for pickup 1, but when I look at the whole problem, you can see how it starts to devolve into sort of your classical global optimization problem. And then of particular interest is when we start to think about, actually it turns out that the more difficult problem and the problem which gives us a greater opportunity for cost reduction is not where to get the tank from, but where to send the tank to get it cleaned, because that's the setup for the next phase. So in this particular example, I have a loaded trailer that comes into a location, and there may be several different locations where I could send it to wash. And if all of those wash locations are feasible from the perspective of the right facility capabilities for that wash site, I have to try to think about, well, what's the best setup for the next order? So this is where we get into forecasting future orders, and I won't talk about that in this session. That's actually one of our enhancements that we're working on right now, is to improve that forecasting so that we can do a better job of setting ourselves up so that when we go to the next order, we're minimizing again empty miles and unused time. So just to kind of give you a perspective of the problem space we're in, I looked at the first 9 months of this year, and we picked up from about a little over 2,000 specific customer locations. We delivered to a little under 6,000 customer locations. In some cases, a location could be a pickup and a delivery. So for instance, if raw materials come in liquid form to a plant and then a finished product comes out, then we'll end up delivering and then subsequently picking up a different product. And then wash locations, there are about 150 that we have agreements with, but in the first 9 months of this year, we used 88 of them. Now, if you count the dots, you won't get to 88, but that's because in some areas there can be several different wash locations that are within a block of each other. And sometimes they have different capabilities, sometimes it's just a different vendor. So this is, I went through and I just pulled out a fairly typical driver and kind of showed what he does in a month. So when this optimization system solves and he gets assignments, you can see he's got a blend of some empty moves. So these are either to a tank wash or from a tank wash, and then loaded moves. And certainly our goal is to have as much green as possible and as little of that orange. Also, kind of looking at a trailer over a little bit longer period of time, you can see that a particular trailer is going to have a journey that can take it all over the country. And this long move from Texas to New Jersey is certainly not atypical. For these products are produced and consumed at very specific locations, so it's much different than our ordinary network, which moves commodities that go to a number of different places. How are we doing on? This is kind of what happens in one day. Actually, after I did this, I realized that it isn't really what happens in one day. It's the orders that delivered on a given day. So this underrepresents if I was looking at a picture of everything that was kind of in transit on a particular day. So this represents if it's deliveries on a day, and the average movement of a tank is 2.5 to 3 days, then this would be about 3 times as dense to give you a visual image of how all this stuff is moving around. Okay, so here's the slide in which I'm going to try to explain how the math works, and then Ashish is going to go into a little bit more detail about the math model and the iterative solve thing. So we tried to figure out how to characterize this as an assignment or a matching problem, and so what we came up with is, so I've got orders on the left, so I've got a number of orders that I'm going to try to find the best solutions for, and when our solver runs, as Ashish will talk about a little bit, we'll be looking at a large batch of orders over a rolling forward horizon of about 5 days. Each order is going to get assigned a tank trailer that is going to be located at some wash facility, so I've indicated that. And then each order is going to have one or more drivers, and the most common situation is 3 different drivers, one to deliver the tank to the pickup location, one to take the tank to the delivery location, and then a driver to take it to a third location. Now, sometimes a driver will go to a location, drop an empty trailer, and pick up a loaded one, so he'll actually be working on several different orders. So suppose I pick a trailer, and then this third column here, what I've tried to represent is the fact that when I'm scheduling drivers to do this work, again, I'm doing it out several days, and I'm trying to optimize not only the tank and where the driver starts, but I'm trying to put together an optimized sequence of driver activities so that drivers don't end up driving a long distance empty. So each one of these strings here represents a possible scenario for a driver. So one of the constraints in the model is that once I select one of those strings for a driver, the other ones are no longer available. So you can see in this particular example, driver 2 might have taken the tank to the pickup location. Driver 3 took the loaded tank to the destination. Driver 3 took the tank to the final wash location. So you can see there are several different decisions here to fit together. And then if I look very quickly at other orders that would intermingle with these, we can see that if things work out nicely, I've managed to use, in this small toy problem, all three drivers to move 3 orders, and each one of them has participated in an order in a different way. So that's kind of what the underlying model is attempting to do when we proceed with it. Just very quickly, so this is the solution process that's actually used by the business. As I said, pricing happens months in advance. A large percentage of this is contract pricing. Then we pick up, we select a trailer, and then go through and select a driver. Ashish will go into a little more detail on this. And then, so this is a decision support system, not a decision-making system. Our goal is to get to about 80% recommendation acceptance, and that's based on the fact that there's always stuff going bump in the night that the model can never take into account. Here's just a screenshot. We probably won't have time to go into this prior product issue, but basically there's a complex set of business rules that are hierarchical that try to efficiently determine if I'm going to put this product in a tank, the first thing I need to do is select down to the subset of trailers that meet the compatibility requirements. And so with that, I'll turn it over to Ashish to kind of go through a bit of the math.
Thanks, Ted. So as Ted mentioned, we have multiple decisions that we have to make. We have to find the trailer, we have to assign an order to a trailer, we have to find the wash location for the trailer, and we have to also find the driver that will be assigned to carry that job. So that is very complicated problem, because even getting to one decision is very complicated. We have to do 4 decisions, and that's why we develop a multi-phase process. In this we have 2 phases. In the first step, what we do is we first generate routes, trailer routes, without any post-wash. So the routes does not have the final wash location for the trailer. And what we do is we solve a math program to find what should be the best way to find more post-wash options that we can add to the trailer routes later. So we use reduced cost and try to rank those trailers that we have found in the previous step, and then we add multiple wash options to the trailer route, and then now we have a trailer that has route orders as well as the wash location. Next, we solve the linear relaxation problem to get the reduced cost to rank some of the routes, as well as the IP to get the optimal assignment for a trailer to order, as well as the wash location after that. Next, we also find some of the work assignments for the driver. Now, so far we only found the routes for the trailer. Now we need to find how the driver should be assigned to those trailers. So the way we do it, we go to the second phase, where at first we select some of the good routes from the first phase and try to generate driver assignments in the next phase. So just to give you an example, if we consider, let's say, 10,000 trailer routes, trailer options, it can generate close to several million driver work sequence. The driver means whatever shipments that driver will cover. So selecting that route is very critical, and we will get into some of the details of how we select some of the trailer routes that will go into phase 2 of driver assignment. So in the phase 2, we first generate work assignments. We use parallel computation, means all the generation process happens in parallel computation, because one of our goals is not to reduce the cost, but also to get that decision in a smaller runtime. So that's why we use a parallel computation architecture to generate routes as well as solve the MAT model. So we generate routes and we solve the combined problem that has the trailer as well as the driver, and get the solution that we want, which is which trailer to select, which order to assign to that trailer, which wash location to get, and what's the driver that are assigned to carry that job. So that's the solution approach that we follow. So now some of the solution particulars that we use. So the business wants to get the runtime to be less than 10 minutes. So not only we need to reduce the cost, but also to solve that model in less than 10 minutes. And the size of the model is very large. So we use a rolling horizon of 5 days. So means we get data for 5 days, we solve the model, and then the time shifts, and then we solve the model again. So we include more than 1,500 orders. We have close to 1,000 trailers and also tractors, which is 500. So if we look into this problem, we get total number of feasible routes that's in billions. And it's very difficult to solve that size of a problem in less than 10 minutes. And that's why we use the parallel computation as well as the multi-phase approach to get to the solution that we want. Now, as I mentioned, we solve this model iteratively, and every time we get the solution, let's say in 8 minutes, we solve that model again with the updated data. So typically in 10-minute time frame, close to 10% of the orders changes. Maybe customer might have canceled the order, maybe the location has changed. So we see close to 10% changes in the order. We also see some 10% changes in the driver locations, means maybe driver is now available at a different location. So that affects 20% of our total routes. So what we also have a warm start feature, where instead of generating everything from the scratch, we can retain some of the solution and the routes from the previous run and only generate the things that have changed. So we have that option that can be enabled if the problem size increases significantly. So now let's go to the hardware and the software that we are using. So we programmed everything in Java, and we also use the user interface that's also developed in Java. We use the Cplex library that is available for Java, and the hardware that we use is very powerful, means as you can see, it has multiple CPUs and lots of cores, and that's what we need for our problem, because the size of the problem is very big. We can get close to billion routes and so on. So that's the hardware that we are using. And just to give you an idea, with this hardware, the generation process for the routes as well as work assignments for the driver, which is what driver will do, can happen in less than a minute. So we can generate and evaluate more than 1 million routes in less than a minute with the hardware that we have, that you see here. So now we look into the optimization model. So we have two types of models. One is a trailer only model, where right now we don't consider the driver at all. It's only trailer, orders, and wash location. And next we'll see the combined model as well. So here we have many cost terms, which is what's the cost for a route, which is how many empty miles a trailer is covering, and all those other penalties that is included. And the constraints are pretty standard, which is the assignment constraint, where we can only use equipment, in our case is a trailer, once. We also need to cover the order, and we also need to have some wash capacity restrictions. So there is a limit on how many times, what's the capacity for a wash location for a week or for a day, and that's also we need to keep track of in this model. We also want to ensure that a particular type of trailer falls at a particular region so that it can cover future orders. And that's where we also have a constraint for that. Next, we move to a driver model, which actually combines whatever we saw in the trailer model, but also a few things that we need to include so that we can connect both models, and then those models will work in conjunction. So now we have cost from the trailer model, and we have additional cost from the driver, because now driver needs to, let's say, come from home to the location where the trailer is present. So there will be some additional cost that will incur. There is also unused hour cost if we are not utilizing the driver efficiently. So we have the previous constraints that we saw for all the trailer problem. And now we have two additional constraints for the driver, where now driver needs to be assigned once, and the work assignments or the shipments that driver are covering, that needs to be also covered. The last one is what combines the driver to a trailer. So we want to match routes that are driver routes to a trailer, and that's where the magic happens. And we need to figure out how to match a driver route to a trailer, and we will actually see some heuristics that we have developed to match driver routes to a trailer. So we use column generation, and we also have some heuristics inbuilt to find at first we need to find the best set of trailers that will go into the phase 2 of driver model. So if you remember, we had two phases, phase 1 and phase 2. And from phase 1, we select some good set of trailer tours that goes into the driver model. And that is the key thing which affects how the solution will behave. And that's where we use the heuristic, where we use some good routes from the trailer model using reduced cost. And we also have some other criteria where we want that the driver should actually, let's say, go home. He should be able to go home at the end of the shift. So we generate some routes that actually will make driver go home, and it will be much closer to their home location. And using this heuristic, we find that this heuristic is very effective. And we find that, so this graph in the x-axis is how the optimal solution is behaving. And we have the cost for the options that was generated for a driver. And we see that in majority of the cases, the optimal solution is typically have a lower cost, which is what our heuristic was also saying, that we generate a good set of routes that have a lower cost. We also saw the same thing for the trailers as well, where the optimal routes are always somewhere in the middle. And the second graph actually gives you a picture of optimal solution for all orders. And we observed that there are very few optimal solutions that have a very high cost, which you see on the right side. And there are many routes optimal routes that have a lower cost. So now for the solver time, again, we use that because of that hardware, the integer programming model and the LP can be solved in less than 2 minutes. Now in terms of project timeline, the project we worked on the project for an year, and we used agile approach to get feedback from the business to improve our model. So now with that, I'll hand over to Ted to talk about the business benefits.
Thank you. So we put this in place in May, and one of the nice things about this kind of a problem is when you have these very clear, well-defined metrics like empty miles and hours used, it's actually fairly easy to quantify in a rigorous way the savings that are associated with what you're implementing. Going forward on an annual basis, the reduction in empty miles based on the period of time that we've gone through, applying very simple arithmetic, is close to $2.5 million. Driver productivity improvements have led to additional revenue opportunity, and the third one, improved retention and fewer hours used, has led to close to $2 million in benefit. And one of the things that's really crucial here is that the better experience the driver gets, the more money the driver makes per time period, vastly improves our driver retention. And the largest and most significant problem facing the freight transportation industry as a whole is drivers and driver retention. So we spend about $6,000 to hire and get a driver out on the road. The turnover rate in the industry for truck drivers is plus or minus 100%, which means if you've got a fleet of 10,000 drivers, you should expect to bring in and get all the way through your hiring pipeline 10,000 drivers a year. We also have recovered 12,000 days of trailer availability, which again has a capital impact. And then we've got a couple of other improvements that we're still working with the business to quantify. So we've got some hard dollar benefits, and we've got some softer ones that we're getting anecdotal evidence for, but not anything we can take to the bank in a meaningful way. I think I'll skip through a couple of planned improvements because I think we're just about out of time. I just want to acknowledge some participation outside of the group that we had there. Great sponsorship from business leadership. We had a couple of additional people in the actually building the software tools, especially the user interface and some of the column generation work. And then a very early phase of the project, we engaged with Princeton consultants and had a number of people help us just kind of get the project moving along. And I certainly want to thank the judges, Russ in particular. We really got some excellent feedback early on, and I think it improved the quality of our written paper as well as our presentation. So thank you.